Meissner. Thank you very much. So it's a great pleasure to be in this beautiful place, and I'm also grateful to the organizers for the opportunity to share my results with you, although I apologize that they are not related to modified gravity. Instead, as the title gently suggests, it's related to the Meissner effect for black holes, which is effect analogous to superconductors' Meissner effect, which describes the expulsion of magnetic field lines from the interior of a superconductor below the critical temperature. Similar effect holds for the black holes, and we prove the theorem which generalizes existing results on this topic. It's a joint work with my colleague from Germany, from University of Bremen, Norman Wilberg. So, before I will state precisely the theorem, I will try to put it into broader perspective why we are interested in Meissner effect and what is more general context. And then I will state the theorem and proof, or sketch the proof. And in order to show you some pictures also, we have to discuss the formations of the Kerr-Newman metric, and this will allow us to plot the transition from non-extremal case to extremal case, showing how the field lines are gradually expelled. Finally, if I will have time, I will briefly address the question of efficiency production in active galactic nuclei and possible impact of Meissner effect on this on the Blandford-Znajek process. So, it's standard to describe the black hole spacetimes by the Kerr-Newman solution, which we believe is quite generic, and it's a good approximation to real astrophysical black holes. Although it exhibits quite high degree of symmetry because it's stationary and axially symmetric, but this seems to be valid for many astrophysically relevant black holes. In addition, it's asymptotically flat, which means it describes isolated black hole, which after all allows us to define multiple moments of black hole, and as seen by observer at infinity, and globally conserved quantities like ATM mass, for example, or angular momentum. But what is a real limitation of Kerr-Newman metric is that it doesn't allow the presence of matter. Okay, it's a vacuum or electrovacuum solution, so in particular you cannot describe accretion disk around the black hole in terms of the Kerr-Newman solution. You have to just treat the accretion disk as a test matter on the Kerr-Newman background, which is usually plausible because the mass of the accretion disk is usually negligible compared to the mass of the black hole. However, accretion disk is necessary for measurement of the spin of the black hole. For example, by iron meter or continuum fitting meter, they both require the presence of accretion disks and some effects associated with corona and so on. But as I said, usually we treat the accretion disks as a test matter on given background, but in fact there are already proposed experiments which might be sensitive to possible deviations from exact Kerr-Newman geometry. And so the question of interest is whether there are some universal properties of black holes, like the no-hair theorem, which hold also for black holes, for example, with accretion disk or with arbitrary sources outside, or for black holes which are not asymptotically flat, but which are an expanding background, and so on. So our general question is, which properties of well-known Kerr-Newman solution are universal properties of black hole, and which properties are specific to this one solution? And we were able to show that Meissner effect, which I will describe in details shortly, that the Meissner effect is one of such universal properties. So it doesn't depend actually on what is around the black hole, what particular solution you use for the description of the black hole, it is always present. So I already mentioned that the term Meissner effect comes from the analogy with superconductors. The role of critical temperature in black hole physics is of course played by the surface gravity, which plays the role of temperature. And the Meissner effect states that also black hole, which is rotating, tends to expel the magnetic field lines, and in the limit of vanishing temperature or vanishing surface gravity, the expulsion is complete and no field lines actually penetrate the horizon. This effect was theoretically observed quite early in 1970 or so by Robert Volt, and since then many particular solutions and situations are known when the Meissner effect holds. But the most of these results exactly considers just the test field on the Kerr background. There are very few exact solutions with strong magnetic fields, like Melvin magnetic universe, where this effect is also present. But no, that these are always just the specific situations. So we tried to answer the question whether we can prove the existence of Meissner effect in a more general setting. The possible implications of the Meissner effects are relative to the efficiency of the jet production. So it's well known that Blandford-Znajek process is powered by the spin of the black hole. So effectively it's energy extraction from the rotation of the black hole. But it requires the flux of magnetic field through the horizon. So if, on the other hand, Meissner effect expels the magnetic field, the question is what is the balance or what is the total net result of these two effects? Our theorem, which I'm going to describe, deals with stationary axisymmetric horizon. I will explain that we need some symmetry in order to obtain Meissner effect. But otherwise, we allow arbitrary matter outside the black hole, including arbitrary sources of electromagnetic fields below the horizon or above the horizon. And also, we don't require asymptotic flatness. In order to treat such general black holes, we employ the formalism of weakly isolated horizons developed by Ashketar and company for purposes of quantum gravity mainly, but it turns out to be a very efficient tool, because you can formulate or easily the initial value problem, which is not given on a space-like hypersurface, but on two intersecting null hypersurfaces, and you can easily see what are the constraints and what are the true evolution equations. So the statement we proved is that any extremal axisymmetric stationary weakly isolated horizon expels both magnetic and electric fields, which is consistent with all previous observations and theoretical observations, but also tells that it's a generic feature of arbitrary isolated horizon. I'm not going too much about to talk much about technicalities, but just to show the essence of the proof. So this H, capital H, calligraphic H, is an isolated horizon, which represents a black hole in equilibrium with its immediate neighborhood, but otherwise there can be whatever. Then we have some other intersecting now hypersurface, which is denoted by N, and these two hypersurfaces intersect on a cut of H, which is a topological two-sphere. And so, in general, you have to impose some initial data on both null hypersurfaces, and then you use field equations to propagate the solution into the interior of the space-time. But in the if you suppose that H is actually the horizon of black hole, your initial data are quite restricted. So all properties of the horizon are specified by the initial data on this spherical cut of H, and the properties of isolated horizon propagate them along H. For example, we employ the Newman-Penrose formalism. I'm not going to talk about details, but A is a spin coefficient which describes the connection of S0. Psi2 is the component of the Weil tensor, which encodes the information about all multiple moments of the horizon. Mu and lambda are spin coefficients describing the extrinsic curvature of H. But for us, the most important quantity here is phi1, which is a complex quantity encoding the flux of magnetic and electric fields through the horizon. So the most of the initial data are given on this initial sphere S0, and only two Newman-Penrose quantities, psi4 describes gravitational field and phi2 describes electromagnetic field, are given on this intersecting null hypersurface. So what we want to show, if we want to prove the Meissner effect, is we want to prove that phi1 is actually 0. Okay? But this is not true in general, because now I said that it's part of the free data. So we can specify arbitrary phi1 and you will get some solution of Einstein equations. So if we ask, or if we require that Meissner effect holds, we have to impose some additional constraints which will constrain the phi1 quantity. In other words, we need some symmetry. So symmetries are described by the Killing equations, and this is the Newman-Penrose form of the Killing equations. But the important point to realize is that these equations don't tell you what are the restrictions on the spacetimes, because formally Killing equations are equations for unknown vector k. What actually imposes the restrictions are integrability conditions for the Killing equations, which, I mean, this is abstract form. You can again project it onto Newman-Penrose now. And that's remaining time? Sorry, that's remaining time? 2 minutes. Okay, sorry. So you have to analyze the constraints imposed by the Killing equations. I will skip the procedure, and at the end you are able to solve explicitly the constraints. You can get phi1 in general. And now, since you assume that the black hole itself is not charged, you will get that the flux is actually must be 0 locally. So not just the integral of phi1, but phi1 must be 0. So it's not a free data anymore. It must be strictly 0 for extremal black hole. And this proves the Meissner effect. Okay, I have more things to tell, but I will skip them. I will just show you the figures. So this is how it looks like. This is a numerical solution for a deformed black hole. So what we did, we extracted the intrinsic geometry of the Kerr horizon and deformed it. So we changed the initial data in order to create electromagnetic source outside the black hole. Then we set the angular momentum to some value. So here it rotates with 50% possible spin. And you see that the lines of the field penetrate the horizon. But as you increase the spin and black hole rotates faster and faster, the lines are expelled from the horizon, and in extremal limit there are no field lines which penetrate the horizon. The same holds for the electric field, and the last figure is with the field lines, because what we saw before was just the lines of equal flux, but these are actual field lines, so they exhibit the same property. They penetrate the horizon, but in the extremal limit they are expelled completely. Okay, that's, I will stop.
So one question. So when you have this Meissner effect, right? You expel these field lines, but these field lines, they are basically tangent to the contour of your black hole. So if you were to perturb the black hole, will these field lines also be perturbed, or they are independent? So do they talk to each other even if they don't They don't interpenetrate them, the horizon and the field lines, or?
Yes, so what do you mean by perturbed black hole? This is exact, yeah, I will answer it. This is exact result because you extract just the initial data and you can perturb the initial data, which will produce the space-time in the neighborhood of the horizon.
Okay.
And if you do perturbation of the initial data, then also the field lines field is changed. Okay?
Now, what I'm trying to say is that if you have, for example, an electromagnetic wave which hits your, so you have a perturbation in your field line which are ejected in extremal case, will that reflect in a deformation of the horizon or not? So do they interact with each other, or they are completely separated because they've been ejected?
They interact, but here we excluded electromagnetic wave through the horizon because the black hole must be constant in time somehow. Okay, so it's an equilibrium. But yes, they interact. So if you take full nonlinear theory into account, there is always this interplay between them.
One quick question.
Yes. Okay, and this is the electric field and magnetic field never actually go into the black hole. You can also generalize any field cannot go into the black hole. Only that's the electric and magnetic field property of.
Okay, so there are results actually showing that the same holds for any test field on a Kerr background, like field with arbitrary spin, including spin 2. So also the linear perturbations are expelled from the horizon. But so far there is no general proof of this kind. We are working on a similar statement.
Okay, let's take part.